that and interject them. So with that being said, John, it is all yours now. So Rob, can you unmute John?
I'm pushing the space bar and it says you are muted. There we go. It says you are unmuted by host. Can you hear me now?
Yes, John, we hear you.
Okay. And can you see me?
No.
And by that, I mean, can you see a PowerPoint slide on the screen?
I see a squirrel.
I'm currently seeing the squirrel.
That's my friend. And so we're going to start off here in the spirit of being locked down and sheltered at home in the spirit of cabin fever, which I think we're all experiencing at this point. And some of us, like my family, like to make friends with the wildlife. And so this is sort of our normal activity lately, is watching the squirrels and birds. And so with that, I'd like to, if I can make my clicker work here. This is interesting. I've not, there we go. So greetings from the Conrad Nut House. Hopefully that's coming through. And hopefully now we can get on to the serious stuff. And you should be seeing a screen that says Rocket Science 102 at the top and is filled up with galaxies and such all the way down to the bottom.
Working fine on my end, John.
Very fine, good. Okay, so we'll move ahead then. As Jeff and Rob have introduced me to be talking about this subject, you probably all, or hopefully most of you at least, remember hearing the first part of this two-part lecture series of what it takes to be a rocket scientist. We talked about getting into space. That was all about boosters and propulsion. And tonight we're going to finish up with first talking about where we go once we're in space and all about orbits and what it is that we have up in space that delivers the goods, if you will, that fulfills the mission. And so over on the right there, you can see some well-known spacecraft. And so without further ado, we'll remind ourselves that the simple mission of rocket science is placing, which is the rocket's role, a payload, which is carried by a spacecraft wherever you want it. And as opposed to what you might think, which would be that rocket science is simply about propulsion, and in a most literal sense, that's true. The whole field of rocket science, which has been widely talked about and referred to for the last 60 years, is really about all of these things and all of the literally hundreds of thousands of people that have been involved in these functions in various ways through the last 60 years of the space age. We talked about the placing part of it in Rocket Science 101, and tonight we're going to proceed forward and talk about two topics, orbits and spacecraft. So let's start off with orbits. And orbits, known to most people with high school physics or even general science probably, are all about gravity. And having spent time with physicists through the years, especially out in Los Alamos, where engineers are sort of, like me, are sort of second-class citizens, you get used to the fact that you hear a lot about gravity when they're describing how they have discovered how things work. And so gravity, as we all know, dominates our life from the time we try to get out of bed in the morning, to going up and down the stairs, to being careful not to drop things. And it is pervasive. It's the universal, all pervasive force. And it is what orbits are all about. As a matter of fact, Newton's laws, which you may remember from this famous 17th century scientist slash mathematician slash astronomer was to not only understand, but mathematically represent how any mass attracts any other mass. And so the attraction of masses simply is the gravitational force, and it acts at a distance such that the further you get away, the weaker is the force. But fortunately, it works well in order to hold one body close to another or pull it against another in some cases. And so we had Newton not only define it mathematically, but give us this handy little figure from his treatise of the system of the world, which came out, I believe, after Principia. And it shows his simple demonstration of what an orbit is all about around a central body. And so he had a mountain at the top of an orb, a gravitational mass, in this case, probably the Earth. And on top of the mountain, he pointed a cannon parallel to the ground. And he fired the cannon with cannonballs with different amounts of energy, such that the trajectory at A, for example, would be how far you would go parallel to the ground before the gravitational force pulled the ballistic object down into the ground, headed for the center of the Earth. Same at B for a little more energy, and eventually, as you get this falling of the ball with enough energy, it's falling over the edge of the world, and in fact has enough energy in it to go all the way around the world, continually, quote, literally falling around the world. And that's an orbit, closed orbit. The more energy you put in from C to D, for example, the higher the apogee, the distance from the center of the Earth in this case. And if you give it enough, then you go out to a trajectory like E, where you can actually escape from the mass gravity. And so this is a simple representation that Newton gave us of orbits that relied on the mutual attraction of masses. So there he was. Before him, preceding him by maybe 40 or 50 years, I believe, was Johannes Kepler, who came up with the 3 laws of planetary motion. Again, a very famous mathematician scientist. In this case, he didn't yet have the benefit of having defined gravity with mathematical representations, but he did have the very good, precise observations from Tycho Brahe, I believe, Danish astronomer who preceded him and who actually employed Kepler at one point to reduce some of the mountains of data that Brahe had come up with in observing the moon and the planets and their motions through space. And what Kepler did simply was study this mass of data long enough to be able to deduce 3 laws, which are quite well known, that have to do with the planets, in this case, prior to gravity being defined, and talked about ellipses and the sweeping of different areas under the ellipse at different times and different velocities and so on. But we aren't going to go into the laws except to note that these 2 men then in the 17th century gave us the underpinnings, and I'll note along with Einstein, but in Einstein's case, who did add to understanding of gravity, this is gravity acting on an enormous scale, which is so small on the scale of the solar system, for example, that we really don't need to use it in calculating our orbits. And so the orbital mechanics that was fully worked out in the 20th century is derived from Newton and Kepler, and doesn't actually need, for the purposes of the kind of orbits that we're doing from Earth, the relativity to be considered. Note that earlier it had been referred to as celestial mechanics, noting the fact that it was based on defining laws that were quite precise, but had only to do with celestial objects, since until the middle of the 20th century, we didn't have any man-made objects in space. But then we did, and each orbit is uniquely defined by 6 particular orbital elements. Now, there are different sets of these that can be used to define orbits, and some of them you're familiar with, like eccentricity and inclination, the argument of perigee, and so on. But I just want you to understand that it takes 6 elements to fully define an orbit such that you can step it through time forward and backward and come up with the precise dynamic changes. That's basically what's known as astrodynamics. Many practical applications for orbital mechanics, all having to do with orbits of various kinds. Some are very familiar, like every time we get in the car and are going somewhere we're not familiar with, we hit the GPS either on our phone or on the dashboard, and it answers a simple question by using the well understood orbits and timing of the GPS system, which we'll talk about briefly in a minute. And then much larger and potentially more important questions like, are those near-Earth asteroids and comets ever going to hit the Earth? Not just this time that they come by going around the sun, but maybe 10 revolutions further down the road in 2033 or something. So far, we haven't found anything big that's going to impact the Earth at the time of our crossing its orbit for the next several decades at least. So those are some very important practical applications. I want to note that the arrival of the science, the rocket science we're talking about, the ability to get objects up into orbit, and the development of digital computers, which started in the 40s and then rapidly progressed, and a particular kind of use of software processing, numerical processing of time-based activities known as numerical integration, all matured at the same time in the middle of the last century. Without any one of them, we wouldn't have been able to achieve what we did rapidly and enter the space age. So now we're going to talk about the classes of orbits, and the first cataloging of them or division of them is quite obvious: low, intermediate altitude, and high, LEOs, MEOs, and GEOs. So we'll talk about each of them. You can see the division of their altitude above the surface of the Earth there underneath each of them. And I would simply note that for the LEOs, it's kind of interesting to understand that while you picture them being way up there in space, many of them are only a few hundred miles up, and since the Earth's radius is 4,000 miles, it's only on the order of, a 20th or so of the diameter of the Earth. And so when you actually draw the orbit, it doesn't look to be that far above the surface, but it is well above the atmosphere. And each of those orbits is well defined for circular orbits as having a period of 90 minutes to 120 minutes, which means that roughly 15 or thereabouts times a day, a low Earth energy orbiting satellite will go around. GEO are all the way at the other end, way out at a particularly special altitude, and everything in between is defined as a medium. And so let's look at these a little more deeply. LEOs in this artist representation, which unfortunately I can't give you a selfie, but this is a probably not too far off representation where each and every little dot there in the cloud, not very far above the surface of the Earth, is one of these space objects. 20,000 plus, it's a very crowded place, and frankly, you're probably aware it's a very dangerous place since all of them have a velocity on the order of 17,500 miles per hour, roughly 10 times the speed of a bullet. And so you don't want to get hit by these things, and that's an increasing problem. But at any rate, of the 20,000 objects, they aren't all spacecraft, they aren't all satellites. About a tenth of them are. Today, I think it's like 2,300 active satellites. And you might be interested to know that the lion's share of them, quite a bit greater than 50%, are the Russians. And we account for about 2/3 of the rest, and the rest of the world accounts for, roughly a sixth of them or a little less. So that's the status of low Earth orbiters. The reason that it's so popular is pretty obvious. The biggest reason is for a given amount of propellant and rocket thrust and a given weight of a payload, or I should say, and a given altitude, you can get the most payload up there in a low Earth orbit. If you want to go higher, you have to cut down the mass of the payload, which will cost you in terms of the mission, or you have to increase the size of the rocket, or increase the amount of or increase the amount of propellant, which means that it's going to cost a lot more to launch it. So in terms of bang per buck, LEOs are the way to go, and it is the way that by far the majority of satellites go around the Earth. It's also good if you're looking down on the Earth, or if you're requiring any kind of signals to be either transmitted or received, because being close means you have the best resolution for any set of optics, or means you have the best signal strength. And then we have this wonderful situation where if you go into a polar orbit, roughly north and south, and the Earth rotates east to west underneath you, eventually you get many repeat passes over the same place on the ground, and each and every place on the ground, as opposed to a lower inclination orbit, which doesn't cover the poles. So some of the common applications, right from the beginning, I think the first weather satellite was launched within 2 years of our first satellite. The meteorology, you get nice high resolution looks at weather systems and CO2 and clouds and water vapor and so on. Another major application, which we talked about in climate change and is very important for other purposes, but especially for that, is earth science, because we can get this complete earth coverage on a repeat basis. Remember, 15 times a day around the world, looking down with a repeat cycle for the data, for the repeat over any particular spot, on the order of 2 weeks in many cases. That varies based on the resolution and the field of view, of course. But at any rate, we get to understand the ecosphere, the health of living things. We understand the hydrosphere, the oceans, the cryosphere, the ice caps and ice sheets, and so on. And without all this repeat data now, and literally decades of it in most cases, we wouldn't have nearly the clarity on just how bad things are with regard to global warming and the changes that are happening. And then in the middle, we have espionage, which used to be something that we didn't talk about. I was in the Air Force. My first part of my career was launching polar orbiters from, and other kinds of orbiters from Vandenberg on the West Coast. And we never would have talked about it then, but I was actually involved in launching some of the Corona spacecraft, the first spy satellites. And so looking down on Earth, listening from low altitudes is all used by many nations with regard to espionage. And then what we can do on board the space station in terms of experiments with chemistry and physics of objects in zero G, as well as actually having people up there for manned visits, is another very valuable application of these low Earth orbits. As a matter of fact, all the manned visits, which now amounts to, I think, over 1,000 people that have been in space, and certainly many scores of years cumulatively, has had everybody only a few hundred miles up, except for those few, 21 in fact, for the 7 Apollo missions that went to the moon, and nobody's gone beyond low Earth orbit since. So I wanted to finish this part just by noting one particularly special orbit, so that you can understand how these things work and what the astrodynamicists are actually figuring out. And so the near polar orbit, you understand now, gives you full Earth coverage, but it turns out with the equations accounting for the perturbations due to the fact that these spheres, known as planets, aren't round, in fact. The Earth is oblate, it's fat at the equator, it's also pear-shaped to some degree, and there are other lower order changes to it. But you put that into equations and you solve them, and it turns out that there's a class of orbits that are very near polar in the 88, 89 degree inclination area, at various altitudes that give you a situation where your orbital plane precesses. It doesn't just sit there in space with the Earth rotating underneath it. It moves slowly as you go around the sun, and you can make the calculations work out and design the orbit so that it rotates at about a degree per day. So in 360 days, or roughly a year, it goes all the way around as the Earth also goes around through its seasons. And what you end up with then is a very convenient situation where, looking down on the Earth, the same local place that you pass at the same local time has exactly the same sun angle and shadow every time you pass it. Extremely useful for scientific analysis and comparisons and stuff. So that's a sun synchronous near polar orbit, very commonly used. So now we're going to go way out. We're going to go out to 22,236 miles, not 230 or 240, but exactly 236 and change. And that happens to be a circular orbit altitude that has an orbital period exactly equal to the length of our day, which means that if we go out there and, in this special case, over the equator, then we are geostationary. We actually hover over whatever longitude we have inserted ourselves into orbit at. And so we seem to be hovering, which is very convenient for some applications we'll talk about. I thought it was kind of interesting to find that the famous science fiction author Arthur C. Clarke, with 2001 and everything, was the first person to popularize this and talked about it, I believe, in the 40s. And it was known as the Clarke orbit for a while before we actually put anything out there. The geostationary at zero inclination over the equator is a special case of geosynchronous, which is the more general case because you can have any inclination, of course, but the same 24-hour orbital period. And instead of hovering, you do figure eights with the north and south of the equator, with the crossing point at the equator. And that's also useful, especially for places that are well up in the latitudes and want to have a lot of the orbit over them, either south or north of the equator. The most common applications are pretty well known and understood. Here is, again, a simple graphic of a bunch of balls, which happen to be close to 200 geostationary spacecraft that are all oriented for various radio uses, relays, communications, cell communications, broadcast, and so on, at the geosynchronous altitude in the equatorial plane, so they're geostationary, and they conveniently are inserted above, you see in red words there, the particular longitude that you want to have them sitting at, hovering, so that you can set up a ground satellite that doesn't have to worry about where it's pointing because the satellite's always going to be there. Just like our dish antenna systems on our houses don't have to be repointed because there it is, it's up there hovering. There aren't too many other really robust applications, but one that we've all seen has to do with watching the hurricane season each year, whether it's over the Pacific or the Atlantic, where you can get the macro scale weather from the geostationary meteorological satellites that give you a whole hemispherical view of the weather systems, and you get to see these cyclonic systems interacting coming across from Africa, for instance. Again, I wanted to end this one with a final kind of special orbit so you can understand some of these things that have been worked out. Way back in the 20s, I think, almost 100 years ago, a German named Hohmann popularized something that another person had come up with years earlier that has then been used very many times during the space age, and it's known as the Hohmann transfer ellipse. And it's a simple way that is used probably more often than any other to get spacecraft out to the geosynchronous orbit. I mean, you picture what it would take for a rocket where the second or third stage was actually going to carry your heavy satellite all the way out, literally 50 times further out than many of the low Earth satellites, and how much extra energy that would take. Well, that's not the way it's done. you insert yourself into an initial orbit, a LEO orbit, a circular orbit, and you've now gotten rid of your booster in your upper stage, and you just have your spacecraft with what's called an apogee kick motor on it. And it has to burn twice. And it burns first, as you see to the left of the Earth there, where it says first burn, and it burns with the thrust downward and pushing the spacecraft now into a higher energy elliptical orbit, the red line. And you've designed the orbit such that the apogee for that orbit will be 22,236 miles. And so when you get out to the appropriate altitude at the design longitude, and it better work out that way because that's where you've been authorized to go, then you fire the motor again with a second burn to add more energy. Otherwise, it would just follow the ellipse around, come back into perigee, but you fire the motor again and it goes into a circular orbit at geostationary. So that's the HOMON ellipse. All right, so in between, as I said, with these many LEO spacecraft. Did somebody say something?
Yeah, John, can I throw in a quick question?
Sure.
Are there any, or could there be a reason for any satellites to be past geo orbit?
Sure. I'd rather try to get back to you with an answer to that, but yeah, there are some.
Okay.
Yeah. I mean, it's not like beyond that you're at escape velocity or something. You aren't.
Right. I mean, those cases, they would actually drift backwards, correct? Because they'd be going slower than the Earth.
Say again?
Anything past geo would actually drift backwards, meaning it would be going slower than the Earth's orbit, right?
Yes.
Okay. Thank you.
I mean, yeah, I don't know that there would be any that would want to do that, although that's kind of an interesting thought. But what the practical application there is, the ones I've heard of are ones that have a lower perigee and a much higher apogee. Okay, so I took your question to mean any part of the orbit. If you mean the whole orbit, yes, you're right. The period would be longer than a day, and so the Earth would rotate and back up, and it would back up on the Earth. Okay, so now we're out to the middle altitudes, very great span from 1,200 out to 22,000. And now we have many fewer spacecraft there. It's the area of compromise, if you will. The higher you go, the greater field of view you have for, say, a signal application, a communications application, as opposed to being down close to the Earth where you go over the horizon all the time. The higher you go, the more generally it costs, although relative to a geosynchronous, it's cheaper. The signal strength is higher than you have out at geosynchronous altitudes, but lower than Earth. And so it's this area in the middle of compromise. And so it just turns out that once in a while, it's not too high and not too low. It's a Goldilocks application that's just exactly what you need. And so somebody comes up with an application, and the ones that are the most common are for cell communications and for navigation satellites. And the cell one, I'll just point out that, you know, the signal strength is better. Power requirements are less, if you will, than if you were out of geosynchronous. The coverage on the ground requires, you know, multiple spacecraft, maybe in the same orbital plane, maybe in different planes. But the most well-known is the one that you see animated here, hopefully, which is GPS. And so the way this little animation works, it's really literally taking the 24 or 20 or whatever it is, GPS spacecraft spaced apart from each other in the same plane times, I believe, 6 different planes, and shows how a point on the ground, and in this case, I think it was Goddard Space Flight Center, it's having an algorithm that calculates how many of those are within the horizon of being at Goddard at any point in time. And so you see that the number of satellites within view is upwards of at least 7, maybe up to 12 at times, something like that. Turns out to actually solve your position equation, you need the 3 degrees of you know, height, length, XYZ, if you will, plus time. And you like to have at least 5 in order to get some precision. These days, most places get many more than 5 most of the time, and so you get very precise positioning out of this. All right, so this particular animation, which I'll put into motion here, hopefully. No, it didn't work. Let me try it again. No. All right. All right, so here we go. You see something NASA produced here, which shows many different altitudes, and by far not all of the spacecraft that are up there right now. You see a lot of polar orbiters. You see some that are in lower inclination orbits, like the Cygnus spacecraft there. As we back out here, you'll start to see things in some of these middle altitudes, like the MMS constellation of spacecraft. And you're starting to see in the right background there, those are some TDRS, telemetry and data relay satellites, just as in the front foreground on the left. And those actually, I'll just stop it here for a second, hopefully. No, that didn't work. The TDRS spacecraft, I'll get them here. So you can see some in the foreground there. They provide the ability for all of these low Earth orbiters that go over the horizon from their ground station most of the time for their 1.5-hour orbits. They aren't viewable by their ground station. And so rather than have recorders on board and store and forward and all that, all the low Earth orbiters have to do is send their signals up to one of these data relays that's always hovering up there and hovering with line of sight access to their ground station. And so it's very convenient for the lower Earth orbiters to use these TDRS, and that's what NASA has them all up there for. All right, so now we'll just kind of follow the line further out than geostationary, and we'll go in towards the sun along the Earth-Sun line. And I'll remind you here of a particular feature of any two-body system that was solved by Lagrange in the 1800s, I believe, the mathematician, who came up with 5 unique places. L1 is one of the 5, where if you put an object there in a two-body system, in this case, the sun and the earth, that the equivalence of the gravitational pull from the two bodies is about equal. And so you can place bodies here and they will be in equilibrium. And we'll see another one of the very useful ones in just a minute. But here you see L1, you see a situation where there's a couple spacecraft in what are called halo orbits, rather than actually being right at the L1 point. And so we'll go in closer to the sun, and then we'll come back out along that same line and see the final part of what NASA put into this animation. We'll come back in, moving away from the sun past the moon, and you can see the lunar reconnaissance orbiter going around there, polar orbit, still up there, 10 years and counting, past the Earth again with all of its many spacecraft, and then beyond the Earth to another Lagrange point. And this particular one, known as L2, is already used by some spacecraft. It's about 1,000 kilometers beyond Earth, so it's way out there. And what we're going to use now is that particular point to put the James Webb Space Telescope in a halo orbit around it, so that it'll be very far from the sun, and it won't use the Earth, even though the L2 points on the Earth-Sun line to block the sun. It will actually be in a halo orbit around L2, so that the Earth and the moon never block it. And that's because they don't want to have the temperature and the radiance extremes that would come from going in and out of shadow. But they will have a multi-layer sun shield that will always protect the optical and the Sirius part of the James Webb from the sun. So that's coming up. It's going to be very exciting when it happens. And so that's about all we're going to say about orbits. And I planted this here to ask Rob and Jeff or anybody else that would like to ask a question. This would be a good time for it when I move into spacecraft. Are there any questions?
So looking at the chat window, there's been a couple, but we were answering them a little bit as we went. There was one question that wasn't answered. It says, you said authorized to go related to orbits. Who authorizes?
I don't remember the context when I said it.
Sorry, I don't either.
Okay. Yeah.
Hey, John, what's
yeah.
the distance to the L2 again?
I think it's about 1,000 kilometers beyond Earth, which is like, what, 600 million? I'm sorry.
Yeah, 1,000
I'm sorry, I
kilometers.
said 1,000, excuse me. If I said 1,000, I meant a million.
There we go. A couple
There
more
we go.
zeros.
Yeah,
A couple more zeros.
there we go. Yeah, a few zeros. That's it. All right, if no further questions, then
There
let's move on.
was one more. He said,
Yeah.
want to put something in orbit, who do you ask?
I don't know. I mean, you know, there are civil, there are, I don't know, any of the agencies that might have use for it, including things like the FAA, I imagine. But I don't know who has the final authority to approve things. I know that there's quite a mechanism, an international mechanism that manages the spectrum for the geostationary communication satellites. I mean, those are all a well-defined orbit. The longitude has to be very carefully defined. And I didn't mention while we were looking at that couple hundred of round balls out there at geostationary, but the color coding on them was for the different frequency that's authorized, because if they're close to each other, you don't want to get crosstalk, and so having a different frequency obviously helps with that. But you know, there are probably a lot of answers to the questions about who you would get authorization from, and especially today when we have, as I'll talk about briefly at the end, a proliferation of very small satellites by non-standard sponsors who can now afford these small ones. And so I don't know what the process is. I will say I don't know that I ever would have gotten to make this comment, but I appreciate the question. I'd like to get a hold of whoever it was that approved Elon Musk's authorization to have something on the order of 10,000 satellites, potentially creating a nightmare for astronomy. I don't know what agency it is or what board it is that approves these things. I'm sure it's there, but I'm not sure it works well. So, shall we move on?
John, one more good question that just popped up. So about
Okay.
the L1 and L2 halo orbits, you mentioned that that the James Webb will orbit the L2 location, but there's nothing there. So what's it orbiting around? Or can you clarify that a bit?
The solution to the two-body problem at L2 would be an exact equivalence of the gravitational pull to hold it there in terms of what's necessary for station keeping. By moving near it, you take advantage of that, and you only need a little bit of energy to keep you in an orbit that can be stable around that point. The math that goes into it is not trivial. It took a very, very long time for anybody to solve the two-body equation, actually.
So it does involve energy, though, to do that.
It actually, yes, it does involve energy, but it is a small amount of energy. And so that's why you were able to do it, because carrying anything with propellant on board that far away is not going to give you very many years of use if you have to use much energy once you're there.
Yep.
All right, so we're going to move on to spacecraft.
Sounds good. Yep, the chat's been quiet, John, so proceed, please.
Okay. And I guess I'm on, okay? So we're going to move on to the area of spacecraft, and we're going to first cover just kind of the general aspect of terminology, that the spacecraft is that thing on top of the booster and the upper stages that is responsible for both carrying, obviously, but also caring for the payload. And the payload is actually what accomplishes the mission. So in a sense, it's like the mother. It's in fact the mothership for the payloads. And when I say payload, remember the word pay, because it costs so much to get these rockets up there and deliver them to these orbits that you better have something that really does pay you back in order to allow you to justify the business case in the first case, and then, you know, hopefully exceed the expectations as satellites, like most of the deep space satellites have done, by exceeding their payback. But at any rate, you got this mothership, the spacecraft. The payloads are any number of things that you're all familiar with, ranging from the instruments that deliver the data, many times imagers or spectrometers or other kinds of measurement instruments, and their radio relays and signal processing, to the kind of spacecraft that actually go to heavenly bodies to probe them, sometimes to land on them, and sometimes to even move around on the surface, and finally to deliver a payload of a person. You know, the astronauts and cosmonauts are all a certain kind of payload, all with their own missions. And so when the spacecraft gets you to the destination orbit, inserts you there, sometimes it deploys the payload, which operates autonomously, but increasingly, I'd say, the spacecraft bus, which holds the payload, which is the instrumentation and so on, is kind of one and the same with the payload, in the sense that it stays with it throughout the operations. All right, another way to look at the breadth of spacecraft is the kinds through the years that you're all familiar with. First, we had flybys, and one of the reasons that we just flew by objects was we were just barely getting able to escape gravity enough to get to the moon or get beyond it to Venus and Mars. And we didn't want to waste a lot of additional propellant slowing down, and we weren't even sure we'd get there, but we wanted to grab some information flying by. So the early ones were like that, and then eventually they got very sophisticated and very high value with things like the Voyagers, where we still have the only close-up visits to the outer two planets, Uranus and Neptune, by Voyager 2. Then we have the orbiters, and these are very prolific, most of them around Earth, occasionally a few of them around the moon, a few of them around Mars. And some of them have provided very high value by going to the other planets. Let's see, out of the 9 planets, which is now 8, subtracting Earth is 7. We've been to 5 of these with orbiters now, since Mercury and Venus have also had orbiters. And we've also orbited the used to planet Pluto, or not, excuse me, we've flown by that one. So the orbiters have given us a lot of payback. Observatories, we especially in this club love things like the Hubble, which for my money is one of the top 5 machines ever built. And then we have those communication satellites serving all of us all the time. And finally, when we get to other heavenly bodies, sometimes we've sensed their atmospheres by actually taking measurements going down through their outer envelope, like Huygens has. We've had landers, some with rovers, and not to be left out, we've had some spacecraft that have visited the asteroids and comets, and in various ways either penetrated the surface to measure characteristics of the composition, or kicked up some of it to observe it, or in some cases actually sampled it to bring it back, penetrators. All right, so that's one way to look at the variety of spacecraft. Another way is just simply to look at, in the last 62 now years since the space age started, how the scale of size has increased, how the complexity has increased. So we'll start, of course, with the one and only famous first one. And here it is. And it's small, and all it did was beep as it went around. Having said that, it did the fantastic thing of being the first man-made object ever taken off the surface of the Earth and kept off of it. So it was a fantastic success for the Soviet Union. Then along came the US trying hard, and we didn't get the second one up, it turns out. That was another Sputnik that got up before we did. but we did have the third, and ours was small also. It wasn't nearly as simple. And so here's how small it was. 31 pounds only, so why do 3 people need to hold it up? Well, it's because they're all pretty important. On the left is Pickering, William Pickering, who was head of JPL, who already in the 50s had been developing rockets for the armies since the 30s, and were responsible for the upper stage on the Explorer 1 here, the first US satellite. On the right is, the famous von Braun. And in the middle is the guy that had the business part of it, if you will, the payload. That's Van Allen, who put some Geiger counters on board and for the first time tested the theory that there's radiation out there, and he found what became known as the Van Allen belts in our very first space launch, much better than just beeping. So now we move way up the size and complexity chain to something sized like a school bus, which you can probably guess is this wonderful machine, the Hubble, and very complex, visited many times by man in order to make this machine, which is the one that's still up there and has many years to go probably, a complete rebuild of what was launched in 1990. Every instrument's changed, the optics were obviously fixed, so it's like a new machine, and it's still working well. And before very long, we're going to have the next generation of that, which is going to have complexity that's challenging even before we get to first light. And by that, I mean the James Webb, and I encourage you, if you haven't ever done this, to go out on YouTube or put JWST NASA in and video and look at one of the animations of this lifting off from Earth and then going through literally 3 weeks of various kinds of configuration activities on board, including lifting up the telescope part at the top away from the bottom part so that you could begin your cooling, opening up the wings of the many segments there. I think it's 18 segments, but they have to be brought into place because they wouldn't fit inside a normal fairing. Putting the secondary out there to face the primary, opening up the sunshade, which is multi-layered mylar, very special material that had to be pulled into tension. All these things are going to go on over a period of days and weeks. And then finally, it's going to get out and go into not the exact L2 point, but a halo orbit at the last minute, where it's going to be a very gentle trajectory there because vibrations really, really matter at that point. You can imagine on liftoff with the booster vibrational domain, it's quite a challenge to make sure that everything is shock isolated. And so that's part of the design of the booster and payload. But once you get out there, you have to be careful not to shake things too much. And so they have a very gentle way to enter the halo orbit. Once it's in the halo orbit at about the end of a month, then begins the configuration of the mirror. With actuators on the back of every segment, they're going to be actually forming the primary, mirror figure over a period of time until hopefully they get it to be perfect. Everything's cooled down, and maybe first light comes within the first 50 or 60 days after launch. And so I don't know, having been through a lot of launches where you sort of hold your breath for a number of minutes or based on getting the payload to make sure it's working for maybe an hour or two, with this, once it's in orbit, that's just the beginning. There are going to be scientists and engineers who have spent decades probably waiting to get this up there that have to wait another month or two to find out if it's actually going to deliver, but it's going to be exciting. So now we're going to talk about what actually is a spacecraft in terms of delivering the functions that carry and care for the payloads. And we're going to use an old favorite, which I love to come back to, and you may remember from the talk about Saturn and Titan. It's Cassini, a huge success, and by that I don't just mean the size, although you see by the people here that it's more than 2 stories in height. One, it's fully loaded with propellants that go in the tanks that are down the center line of the vehicle and hidden from view here. It's got 3.5 tons of propellants, or 3.25 tons, and a grand total of about 6 tons. The largest mass payload or spacecraft ever launched that was successful. The Russians actually launched 2 that were bigger in the 80s, both of which failed. And so we have the most successful one that, you know, by size too. And so the trajectory, interestingly, in order to get this mass out roughly 900 million miles, about 10 times as far away from the sun as the Earth is, we had to actually travel 5 billion miles to get out that billion miles. And that's because we had to use the gravity of Venus by going around the sun and Venus twice, and then Earth, and then Jupiter. So it took 7 years to get there. Once it got there, it went into an orbit that was only a Saturn orbit. People might think because it visited all these other moons that it went into orbit around other things. It didn't. It just had so many orbital changes that were targeted at various points after it had its close approach to Saturn to go by this moon or that moon. And in over 100 cases, it was going by Titan. And so another 13.25 years were spent out there by Cassini. And the results were fantastic when the mission was completed roughly 2.5 years ago, and we deposited it into the outer envelope of Saturn with all that data, moons that have been discovered, and I'm sure at this point, many more than 4,000 research papers, because this slide's about 1.5 years old now. All right, so we're going to talk about what it takes to be a spacecraft in terms of the various systems. Obviously, you need brains. And it's kind of interesting to think about this, but this spacecraft that still was being very successful just a few years ago, after being launched in '97, designed in the early to mid '90s and built with computer technology back then, look at the RAM and solid state storage there, you know, on the order of, you know, the laptop I'm talking to you from has roughly 250 times as much, you know, solid state storage as the Cassini spacecraft did. And it had all these instruments on board to gather data from. So obviously some of the critical features were that you could upload code, and you needed that, of course, for all the different orbits that were changes that had to be designed on the fly to meet the scientists' requirements. I mean, you can imagine halfway through 13 years, there were plenty of scientists that had taken early data, come up with other things they wanted to see, and moved up the priority list until they got to send up another load to change the orbit again to help them. Data from the instruments, many instruments had to be stored and then forwarded back, as you'll see in the communications part. And it was the first spacecraft that ever had a fault protection mode built into the software, which was called into play autonomously 3 times when the spacecraft got into a situation that it was confused by or thought something was wrong and wanted to let the people on the ground have a look at what its housekeeping data said and say, do you want to do something? Is everything all right? And so it put itself in safe mode several times. And there are other computers and controllers in the stellar reference unit, you know, for pointing and so on, reaction control system. And then there are these other subsystems, and we'll go through them quickly. What I did want to note is, with the multi-billion-dollar kind of spacecraft we have for deep space like this, and once in a while NASA figures out a way on one of their special programs that's supposed to make things more affordable to do a whole planetary spacecraft for under $1 billion. But that's pretty hard to do these days. At any rate, the point is, it's going to go out there and you're never going to be able to touch it again. And so there's lots of redundancy on these spacecraft. Whole systems, like the thruster system for pointing and steering, are doubled up on so that if one of them fails in a multi-year mission, you can just kick in another one. You're going to hear about that a little more. Mechanical subsystem might seem very easy, very simple. It's actually got quite a lot of things built into it. For starters, there are a number of things called ground support equipment that are built customized for the particular spacecraft design, like lifting fixtures that will never fly and never be used again probably, but are needed for that. Not inexpensive, and it's part of the mechanical subsystem. The main part of it is whatever kind of a spacecraft structure or bus is designed, usually with some struts, with some faces on it, with some isolation of objects, and perhaps pre-designed modular fittings to fit things to. But at any rate, that's the main part of the mechanical subsystem. And then finally, a very key part down at the bottom here, usually conical shaped, and it is the thing that takes you from the geometry of the top of the booster or second stage to the geometry of the diameter of whatever spacecraft you have, which changes all the time. So it's custom designed. It's got a lot of specialness to it in the sense that every booster creates a different launch environment in terms of shock and vibration. And so you have to account for what kind of protection you need to have to shield the spacecraft from that particular violent environment on liftoff. Then we have the thermal subsystem. Again, seems fairly simple, but it's quite challenging and pretty busy when you look at it. The most exciting part to me always was the part at the top here, because when the technicians showed up to wrap these special cut foil multi-layer blankets around various members and surfaces of the outer spacecraft, that meant you were about to put the spacecraft in the fairing and get ready to launch. So you'd probably been through months at this time. This is like the last thing that happened. And so this was all designed to give you some passive thermal control. And the reason you need so much thermal control is because when you go from seeing the sun to seeing deep space and being shielded from the sun, you're going through swings that happen almost instantaneously sometimes, and do in fact for Earth orbiters. That is the swing from, over a span of about 800 or more degrees Fahrenheit. And so the amount of expansion and contraction, the amount of challenge to keep things at room temperature, as it says there. And so these blankets help, but you also have all kinds of heaters on board reacting to the thermostats if they say it's getting too cold, or if the stuff's heating up and the instruments are generating too much heat, you have louvers that open and let you radiate heat out, safe modes if it gets too hot or cold. It's quite a busy system, the thermal subsystem. Okay, so now we're looking at that two-story Cassini stack. And the one thing that you may have noticed that you don't see, that's very familiar for all the things you see when you look up in low Earth orbit, which is kind of like wings, picture the Hubble or the space station, you don't see solar panels because you're 10 times further out, which means the solar radiation is 1% of what it is in Earth orbit, and it's not enough to give you much energy out of there. And so what they settled for, as they often do for the longer term and the deeper space missions, is these things that are colloquially called nuclear batteries, radioisotopic thermoelectric generators, which take advantage of the fact that the thermal decay of radioisotopes gives off heat. And for the carefully selected plutonium-238, the half-life, the amount of time it takes for half of it to decay is quite long compared to a spacecraft life. And so even for 20 years, which is what Cassini had from liftoff to end of mission, you still have a fair portion of the 73 pounds that was loaded into these 3 RTGs and mounted at the base of the spacecraft by the end of the mission. So with no moving parts, you get this decaying heat energy with thermocouples turned into electric power, and you get an electric budget. And it's all the electricity you have out there. And you look at that number and it isn't much. 880 watts, a few table lamps worth of electricity at launch time, which decayed down to about 600 watts by the end of the mission. And for that, you have to operate all the instruments. You have to keep your reaction wheels spun up. You have to process data, commands, you name it. So the planning activity that goes into carefully using, budgeting your power and turning things on and off is really quite an exercise. And you can imagine if you never understood why, if you ever looked at a NASA budget, what there's a cost for spacecraft operations. Now that you understand 300 orbits around Saturn, most of which were different, and hundreds of flybys of dozens of moons, and all the different pointing as well as the downlinking and the uploading, the amount of activity that it takes to plan all that out and load it into commands is requiring lots and lots of people on the ground for all of those 13 years on station. So now we're into the propulsion subsystem, and here's an artist concept, if you will, that just kind of gives you now finally the highlights of what weighed the most on the spacecraft. And so down the center line are these two tanks, top and bottom, with hemispherical domes, and one of them is fuel and one of them is oxidizer, and they were required for, and I flip back to this so you can look at the red bells at the bottom there. Those are two rocket bells, if you will, for the propulsion system, the main propulsion system for the Cassini spacecraft, not only for getting there with the orbital changes, or I should say the trajectory adjustments on the way, but once you're in orbit. This all came from firing the main engine over and over again. This is a very tried and true engine, the R4D, 183 firings, and it had completely redundancy with a backup there on the right, which was never used. And so very highly reliable main engine. The other kind of propulsion came from fairly substantial thrusters, sets of 2 each on each of these 4 legs, give you roll and pitch and yaw as you command it. And each of the 4 legs also has a complete backup set for a grand total of 4 on each of 4, or 16 of these thrusters, 8 in use. And they actually did fail the primary set, I think in 2009. So for about half the mission they worked, about half the mission they used the backups and they worked fine. So redundancy saved the day. The final thing I'll talk about is simply what feeds these propulsion jets. And in the case of the bipropellant for the fuel and oxidizer, we have multi-methyl hydrazine and nitrogen tetroxide, which are pretty serious hazardous things. And it was that over 6,000 pounds of those at launch that was the determinant of the end of the mission, because you couldn't go and change orbits or steer certain ways once that stuff ran out. The other propellant was the monopropellant in that round tank on the side, and that goes with the thrusters, and probably they had a I don't know, catalyst bed or something that they ran the monopropellant through to fire the thrusters. But at any rate, it was the bipropellant tanks and that fuel and oxidizer that determined when they were out of gas. Oh, there's one more tank on board, and this is typical of every spacecraft I ever saw, and it's usually helium. Helium is used to apply pressure on top of the emptying propellant tanks so that you can maintain the proper pressure as they go out through the nozzles. And so that had to last through the mission as well in order to keep the tanks pressurized. So finally, they got near the end of the propellants, they planned the finale, and by the time they dropped it into the Saturn envelope, they'd used up all but about 1% of their propellant. And that defined why it was in orbit for 13.25 years and not 14. All right, so we're getting near the end here. How do we get, yes, go ahead.
Throw in a quick question. A question was about the sensitivity of the plutonium on board, and that you mentioned there's some concern about launching plutonium.
Yeah,
I
wish I could remember the exact numbers. It's a good question. I was going to mention it, but I'm trying not to get too much detail. At any rate, every time you launch one of these things with radioactive materials, it's a very serious question that has to be answered as to whether or not you're going to be allowed to do it. And it's a calculation that says 73 pounds, very, very dangerous stuff. Whether it's at 1,000 feet just after liftoff, or it's at 50 miles before we achieve orbital velocity, if some catastrophe happens and the worst happens and this stuff actually is exploded and dispersed into the atmosphere, where it'll be entrained and it'll be up there for years with this half-life. And so with that additional load to the, and this kind of calculation actually started back at Los Alamos, not for rockets, but for nuclear tests in the atmosphere back in the 40s and 50s, because people were really worried, for good reason, about putting too much of this stuff in the atmosphere. And it turns out that you can calculate what 73 pounds will mean in terms of the change in the risk of certain kinds of cancers to certain populations years after that disaster might have happened. And so you actually estimate how many people will be lost if there is a certain kind of disaster, and make your decision based on whether or not that's a low enough risk to accept. And they screwed up the calculations the first time for Cassini, and they had it off, I think, by 2 orders of magnitude.
Ooh.
Anyway, I wish I'd gone back and reviewed this. I knew this cold a year ago. It was like 5,000 people, additional people were going to die within 20 years or something. It's completely unacceptable, but they finally figured out what the number should have been, and it was a small number. And so they accepted the risk and they launched. And like I say, they did it for, the Jupiter spacecraft. They did it for New Horizons out to Pluto, anything with these RTGs.
Cool.
All right.
Hey, John, if you don't mind, another good question just popped up, which is, could you speak a little bit more about why they dropped it into Saturn?
The short answer is they don't want it to be running out of gas in a way that they can no longer control it, and having the chance of actually polluting a moon or something like that. They obviously aren't worried about polluting Saturn, because that's where they let it be basically vaporized, okay? One can say it's a matter of scale, but they didn't want it, 23 years from now landing on Enceladus or something like that. So that's the short answer. They've done that with all of the deep space large spacecraft.
There's another question about, does the propulsion system eat into the electrical budget?
I'm sure that the relays that, I'm sure there's a little bit of electrical usage. The answer is I don't know. There could be an electric pump for the bipropellants, for the main engine. I think it's probably a very small usage. Okay. All right, so we'll get on to the communication system, which has this fancy TT&C name, which you can see there. And basically, you have this really visible thing on Cassini, which catches your eye immediately when you look at it, this great big white dish on top. And that is the central part of the communications with Earth. It's a high gain antenna. And it happens, by the way, if you happen to remember this, to also be the active part of the synthetic aperture radar system, which they pointed at Titan over and over again to paint these swaths on the ground and see through all the nasty atmosphere on Titan. But so it's a very dual use, very valuable thing, a high gain antenna. And in the middle of it, you see a low gain antenna, which is the backup for it, which never had to be used because the high gain antenna worked fine for the entire mission. And so what it's used for, and you see in the asterisk down there at the bottom, a figure that might surprise you. Every day they spent hours with Cassini pointed back towards the deep space network on Earth. Those great big dishes, 40-meter dishes and things like that, both collecting downlink data and also uplinking the commands in the code that might have to be used to change the way things operated. And so it was a very serious activity going on, and it says nominal. So I think I said every day. It probably wasn't every day, but it was an awful lot of them. And when they did it, it was a long time that they spent staring back towards Earth. And all the rest of the communication stuff is boring and buried in the stack here, but you can imagine the transmitters and transponders and receivers and what conditions the signals from the various instruments so that they can go into the data stream and so on. And so here's yet another look at the TT&C. Where am I here? Okay, I'm sorry. I'll get to that in just a second. In the context of the navigation system, I forgot where this slide was coming up. So now you see, and just think about this for a second, you have a two-story observatory here. None of the instruments are gimbaled. They're all hard mounted. And so the VIMS, the visible IR, spectrometer is pointed in one direction. And in order to get that to paint the surface of Titan, which they did over and over again until they painted it completely, you have to steer the entire stack around and open the aperture at the right time, at the right altitude to take the planned data, and so on and so forth. The high gain antenna for the SAR means that you have to turn this whole thing over and point it straight down at the ground as you do your closest pass to paint these swaths with your radar in the ground. And so you can picture now this entire two-story thing going through this ballet in space to turn things so that different measurements can be made by different instruments at different target points as you pass by different moons and so on. Quite an exercise. And the steering and attitude control is pretty special, and it worked perfectly. For pointing the antenna, and by that I mean this large high gain antenna, we took advantage of the sun. And by that I mean you see a sun sensor up here, mounted, highlighted in yellow, mounted on the back of the dish, looking through the dish along the longitudinal axis, finding the sun. And why do you care about the sun? Well, when you're that far out in the solar system, the Earth is pretty much in the direction of the sun. It's just one of these near-in planets going around the sun with not much excursion to the right or left. And so if you can find the sun, you're most of the way there to now tuning into where the deep space network antenna is and finishing up your pointing to that for your data pass. You also have a couple telescopes mounted on the right side there labeled stellar reference units. And they're just fixed mounted, redundant. They have on board a stellar reference unit, I should say a star catalog of obviously many stars, and we can all appreciate that from what we do under the night sky, such that you open up the stellar telescopes there and you just let the field of view look through your catalog until you have come up with the requisite number of points for a certain degree of precision, and you have locked on with great precision to exactly what your inertial reference needs to be. And so that's your primary reference. You have the 3-axis gyroscopes that have been around since the beginning of space travel, but they generally weren't used because the star tracking system was so much more accurate and it worked all the time. And the gyros weren't needed to be used as much because of what you'll see in a minute known as reaction wheels. And so you have to, and then you can point and you can steer, and the steering capability comes from the two things we've talked about with the propulsion system. One is the main engine, which is gimbaled, so you can get some steering for changing your Saturn orbit, for example. The other, and much more commonly used steering mechanism for the large scale movements is those thruster clusters at the end of the 4 legs to roll and pitch and yaw as you need to move the spacecraft around to get the right instrument with its aperture pointed in the right direction on the target. And that was used not a lot for much of the mission, except when they were near Titan, when they had to go through some very large changes in pointing in a hurry. For what I said before, the VIMS and the SAR were the two major instruments, and they were very different pointing for the whole spacecraft mass. So finally, that brings us to these wonderful little spinning momentum wheels, if you will, reaction wheels. I don't know if you've ever heard about these or heard of control moment gyros. If you think of your bicycle and spinning it and how it gives you stability, if you ever played around with a gyroscope, you know how that works. If you ever took a course in mechanics, you're probably familiar with precession and with the torque that's produced applying a force, you know, at angles to a spinning gyroscope. At any rate, the reaction wheels work on this principle. Here is one of the reaction wheels. There were 4 of them on board, mounted at different angles, hard mounted, so that they would account for the 3 axes of the spacecraft. And the 4th one was redundant, and in fact, one of them failed, so the 4th one was needed, but they had these 3 running. And basically what happens is you spin these up, it's quite a heavy mass, and you spin it up just like a gyroscope, and it's very stable. You see the pointing stability there over more than 15 minutes. It moves almost not at all. And by changing the spin rate, you actually apply a torque in a certain way. And so you can use these 3 with changing spin rates in order to steer the entire massive vehicle. And that worked out very well for the entire mission, except when you needed to do things in a big hurry. And, whoops. And in fact, the operation of these reaction wheels has kind of gone down in the history books. There's never been, you know, these kind of mechanical wheels that have spun that much and been turned on and off, again, going back to the electric budget, that many times and worked perfectly for 20 years. So it's pretty impressive stuff. All right, so we're done with Saturn, I should say Cassini. We're on to the bigger question, which is what are we actually going to do in the future, since a $4 billion space mission is not your everyday thing. You're going to do more of them. Probably a little more infrequently, I would guess, but I'm not sure. I mean, every year the Trump administration has been trying to cancel the W1 space telescope, and Congress has been putting the money back in. They've tried to slow down the James Webb, which of course is years behind schedule already. And my point is that even the governments with the biggest budgets view these as hugely expensive, and do we really want to do that? And so the pressure has grown, and the small users at universities and corporations that want to use space have really gotten into the act, and they've driven a growing revolution in spacecraft, down towards spacecraft that will have all the same functions you just saw, but in an extremely small envelope and an extremely small mass. And the only way to do that saves money is to try to come up with modular approaches to doing power. You know, so for example, a cube with solar cells on the sides, standard kind of computers, and that's easy to come by. They're even off the shelf now. Any kind of chip computer and high-speed processor you can find. So these things are modular, they're repeatable, and they're small. And so the revolution looks like things like this, with names like small sats and nanosats. The classification of them by weight, you see from this article, I just pulled this out of a Wikipedia article. And if you aren't familiar with metric, you just multiply everything by 2 roughly, and you get the pounds. So any kind of satellite that's less than about half a ton, less than 1,000 pounds, is in the category of a small satellite. That's the general title for all these. It's also the title, along with mini satellite, for that range. And then coming down by the various steps here. You see the different ranges. It turns out that the most popular range now that's been used, and it's been used a lot, you'll see, is nanosats. 2 to 20 pounds roughly. You can get a lot of functions and a lot of payload capability out of that particular weight. If you go to the website that you see staring at you on the bottom here, that the Europeans keep nicely up to date, nanosats.eu, you'll find wonderful graphics and statistics there that changes all the time. They keep up to date. And so I got the latest from January. There have been now, since the first launch, I think in '98, 1,300 plus of these nanosats have been launched. Now, they're launched in bunches sometimes, or at least multiples. This many countries, if you can see the numbers, the small numbers there, for example, if you see, I think Chile has, I can't read their number. I can see Peru, yeah, Peru's is 4 and Ecuador's got 3. Anyway, you see some unexpected countries that have nanosets because they're small and cheap and they can finally reach the ability to have a budget for these. The US, as you see, has about 2/3 of them that have been launched, and China and Japan are up there. Most of the nanosets have been CubeSats, which we'll look at for a second. And you see the number of companies in the database that this website has for building different aspects and different structures and different functions in these nanosets. And it's got a very familiar feel to what the internet world was like in the '90s. There are all these unknown names you see popping up as companies. So we've got a huge number of small companies proliferating, trying to get at the market, because the forecast is there are going to be a couple thousand more of these in just the next few years. So if you can get in there with a modular capability, say for data processing of certain kinds of payloads, and people will always buy that standard form and that particular weight, you might be able to sell hundreds of these. So the volume opportunity is there and companies are going after it. Modularity, commonality, that's what it's all about. Here in the foreground of the table, you see what you've probably heard about, CubeSats, and engineers love to throw around the term form factor. And so again, you go into the definitions and you'll find that the 1U form factor is this cube, about 4 inches on a side. It's metric, so it's actually 10 by 10 by 10, but it's about 4 inches on the side, about the size of a Kleenex box in your bathroom, and no more than 3 pounds by definition. And so you've got various geometric configurations of this 1U form factor put together in different ways. If you stick it into that erector set thing you see on the back of the table there, you can get 3 of them in there. It's called a P-pod. And so you get 3 1Us in there. They might each have a different function. They might be independent payloads. And that P-pod is capable of kicking these out at different places in the orbit, wherever the customer wants them to be. And there are certain kind of functions that the P-pod has on the outside of its structure that it performs. And you've got other things up to 12U, which would be a configuration perhaps of 3 by 4 of these or something like that. And the other thing that allows you to drive costs down, which has been a push by the government since the '80s really, when we started finding that you didn't actually need a Sun workstation, you could get by with an Apple off the shelf. And so I actually put some of those into a ground intelligence system back in the '80s and took up the challenge of COTS back then. But commercial off the shelf is a key way to get at affordability, which is really what this is all about. They're affordable enough that over 90% of the customers are non-standard customers. They're universities and companies that want to get into the action, either proving out a concept, giving their students a chance to do a little space research, developing some functional capability with a demonstration unit so that maybe you can market it as a company before long. And the government and the military, the typical, billion-dollar budget kind of government customers haven't needed to, pay much attention, and yet they've found good uses for them, like the the two CubeSats, trying to remember the name, I think it was called MarcoSat, that were used to relay the landing of the latest Mars lander roughly 6 months ago. And so everybody's going to get into the act. People are really happy to have the opportunity to take advantage of these modular capabilities. The vendors are proliferating because, like Elon Musk, like what's it called, OneWeb, which was another customer that was going to put up hundreds or even thousands of these small satellites over the next few years for, I believe, telecommunications, cellular. It actually is a victim of the coronavirus already. They went out of business a couple weeks ago after launching some of their early ones already. But at any rate, they're going to be big customers with big constellations. And it's a young market, and it's just kind of crazy at this point. It's going to be decades before it sorts out. And it's sort of like I was very much involved in the late 90s as Lockheed's director of electronic commerce in, working with lots of companies you've never heard of to try to figure out how to make money in that market. And then the internet bubble burst and most of them went away overnight. Well, I'm afraid that this particular feature right here may be causing quite a step change in this young market. We'll see, just like we'll see about every other thing here, hopefully within only months, but it's going to take a while to sort out and see what business is like and what companies are left, maybe especially in immature markets like this with a lot of small companies. All right, well, that's it. You folks have earned this. Thanks for your attention. Congratulations, and my favorite robot joins me in asking for questions.
So John, thank you very much. I just want to do a quick 30-second plug. Appreciate everyone that joined us here tonight. A special appreciation to John. Hope to see a lot of you in our usual Tuesday gatherings, get-togethers. And then especially hope to see a lot of you at our meeting, our normal meeting in May, where again, Professor Ben Marucco from the University of Delaware will be talking about his research on the sun. So John, in terms of questions, maybe at the risk of some dabbling in some chaos, to make this a little bit more dynamic and interactive, we'll allow people now to ask rather than type the questions. If it gets too out of hand, we can jump in. But if anyone has a question, please go ahead and unmute yourself. And hopefully, if things go well, it won't be a big cacophony, but let's give this a try. It'd be nice to hear some voices other than John, mine, and Rob's for a bit. Does that sound all right, John?
Sounds great.
Cool. Again, if anyone has a question, please unmute yourself and ask away.
So, John, what do you think the most interesting application of CubeSats has been so far?
I am not an expert. I've been a newcomer to this, and I'm not really a good person to answer. The best one that I've known of, because it happened to support a NASA mission in a major way, was that communication relay that allowed us to actually witness the soft landing of a Mars mission where the other Mars orbiters were not in the right position to get us that information. And so the MarcoSat two-satellite combination last year was the most interesting I know of, but I actually haven't looked into this that deeply.
Very good. Anybody else? Again, please unmute yourself. Ask away.
I thought this was a wonderful presentation. Is there any way you can post the PowerPoint?
I recorded it and should be posting it if it works out.
Okay.
There you go.
John, just for a more compact version, would you have any objection to us getting your PowerPoint slides?
I'll think about that. I generally don't do that.
Okay, fair enough.
But I will think about it. I might.
That's a fair enough answer. Thanks, John.
Yep.
Anybody else?
There was one earlier They were asking how accurate did the antenna have to be coming from Cassini back to Earth?
Wow. I'd be happy to get that figure for you, but I don't know off the top of my head.
Give him a round of applause.
Yep. Any other questions? Final questions?
No, that was a very good presentation. I can tell how hard you worked on it. Wonderful job.
Thank you very much.
Thank
Glad you
you.
guys
Great.
enjoyed it. Stay
So,
safe
John,
and, yep.
If you don't mind, I'm gonna. So, any final questions? Just give one final chance to anyone else that has a good question.
No, I
If
thought it
not,
was
I hit the wrong thing. Sorry.
hang on one second here.
Ah,
Bear with me here. Yeah, so if not, on behalf of the entire DAS, John, thank you very much for a great presentation, and especially thank you for being our guinea pig in our first Zoom meeting. I was keeping an eye. We had upwards of 39 people participating, so that's quite excellent. And including, I won't call out any names, but a couple of members that we haven't seen a whole lot because they live a bit further away. So kind of neat that the Zoom provided an opportunity for that. So let's do another really great experiment now. If everyone wants to go ahead and unmute themselves, let's end with a good round of applause for John.
yeah.
Yay. Thank you so much, John.
I love it.
Thank you.
Thank you very much.
Yeah.
And again, thank you, John. Thank you, everyone, for participating. I'd thrown a note in the chat. Whoop, what happened here? Oh, okay. If anybody has any feedback or comments or ways that a Zoom meeting such as this could be improved, or if anyone wants to share any special challenges that they had, by all means, feel free to email me. We want this to be inclusive, and any feedback that we could address could be corrected for future Zoom gatherings.
All right, and also I wanted to
That's good.
share this. So if you look right now, it's fairly clear outside, and it's actually looking pretty clear for a good while this evening. So
Yeah.
if you do get a chance to go outside, you can observe just like we would from the Samhain, you know, after a meeting. You can go outside and take a look. You can also get some snacks. We don't have any to offer, but, you know, maybe you have some in your kitchen. And go outside, look at the beautiful skies, and have some cookies.
And maybe a beer.
Sure.
Wait,
I got
Rob, per usual, Diana has offered to share some snacks with us.
Right.
So everyone, please help yourself.
Looks delicious.
Cool. Well, again, I would certainly welcome, again, big final thanks to John. And certainly welcome people who want to hang out a bit longer, chat, hang out. But again, all in all, really good. Appreciate everyone's participation here.
Thank you. Thank you.
Fantastic.
Good stuff.
Okay, thank you.